Hello everybody, my name is Abdellah Tounsi, PhD student at University of Monterrey Consulting 1 from Algeria. I'm happy to be with you in Quantum Africa 6 conference. My talk is going to be about topological compilation of 3-qubit gates. So we are going to talk briefly about topological quantum computing and onions, and about topological single qubit gates because they are important to construct topological 2 and 3 qubit gates. At the end, we'll end up with some results and conclusions. So the main idea behind topological quantum computing is to store the quantum information in the topological property of the physical system, which is essentially a non-local order parameter. The purpose of this is to protect the information from local quantum errors. One way to do that is to use onions, which are quasi-particles with statistics more general than bosons and fermions. Onions lives in two-dimensional space. Because in two-dimensional space, exchanging identical particles falls into two topologically different classes. The path of particle going around another is topologically different if it is in class A or B. So as a result, the quantum state of onions is determined by their topological arrangement in the surface, and their evolution is governed by breeding operations, which are independent of dynamics and geometry. So the advantage of breeding operations is laid in their topological nature, which is not affected by local perturbations, as shown in the picture. So in the breeding group, we have clockwise and counterclockwise exchanges of anions. Before calculating breeding matrices, we should define the anion models, which involves different types of anions, like the vacuum zero and other types of anions, and defines also the fusion rules between two given anions from same or different types. For example, when we fuse A and B, we can find many possible outcomes, and each outcome has different ways of fusion. So the simplest, one of the simplest anion models is the Fibonacci model of anions, which includes the vacuum zero and the Fibonacci anion one. When we fuse two Fibonacci anions, we get the vacuum or just another Fibonacci anion. So the all possible fusion states given three Fibonacci anions are these three fusion states. We can pick two of them as a computational space. They are the computational space because they have the same overall fusion, which is one, in order to not mix it with non-computational space. In the same way, we can pick two quantum states to form qubit with four Fibonacci onions. We have now three non-computational states with overall fusion one. Interestingly, the dimension of fusion space in Fibonacci model follows the Fibonacci sequence. As a result, the fusion space does not have the tensor product structure like qubits. So it's a bit different. Without going through all calculations, breeding matrices. Given three Fibonacci anions, we have sigma 1 and sigma 2. These are the explicit values of sigma 1 and sigma 2, where the blue matrices acts on the computational space. We see that the computational space is not mixed with the non-computational space. And what is important here is that it is proven that the group generated by sigma 1 and sigma 2 is universal, and we can approximate any SU2 matrix. In the general form of breeding sequence with sigma 1, sigma 2, and their inverses is given in this picture. So we have the blue matrix in the sector 1 and the red phase in the sector 0, and the global phase of each sector is determined exclusively by the winding number, which is the sum of breeding powers, and we have the core SU2 matrix. The question is how to find the best approximation of given unitary target with breeding sequence. One answer is Solovay-Kitaev algorithm because it ensures that this approximation process is efficient in polylogarithmic time. So the basic idea of Solovay-Kitaev, which is an iterative algorithm, in each iteration, we try to approximate the target U with U0, and we get C, which is the U0 dagger. The second step is to involve the group commutator decomposition of C to A and B. Then we approximate A and B with a basic approximation. Finally, we get a better approximation of U with U1, which is a combination of A, B, and U0. So in general, approximating A's and B's in Solovay-Kitaev algorithm needs a pre-processing step with brute force algorithm in order to enhance the basic approximation epsilon 0. We tried to optimize the brute force algorithm using algebra and some technology. The first thing we should know to optimize the algorithm is similarity relation. We start with the last equation, which says that sigma 1 is similar to sigma 2 with the F, which is called the fusion matrix. This is proven for 3 anions in all anion models. We can prove that. So in general, by recursion, we can deduce that any breeding matrix, if we exchange sigma 1 and sigma 2 without changing the powers, we have a similarity relation between them. So we don't need to recalculate the breeding. The second property is a simple theorem. Given if the target unitary is a Hermitian, let us call it H, and a given bred B, the distance between B and H equals the distance between B dagger and H. It is obvious if it is equal the B distance between B and H dagger, but this theorem says that it is equal to the distance between B dagger and H. So if the target unitary is Hermitian, we should not include the inverse of the breeding sequence. So we have reduced the search space by 2. The other thing is since the winding number determines the global phase, we should only focus on the SU2 matrix, which is a rotation in the Bloch sphere, and every rotation is a quaternion with four real parameter instead of SU2 matrix, which has eight real parameters. Quaternion is simpler to compute in CPUs. From technological side, we should use an efficient programming language like C++, which still among the three most efficient languages in terms of energy and time, and we can do better if we use more efficient languages. The last point is to distribute the search space of breeding sequences over the given number of CPUs in the computing machine. This is an example of Hadamard. This is the optimal approximation of Hadamard with 30 breadths, and this is the obtained matrix. We have after in the first time we have coded the program in Python with distributed processing only. The processing time was 40 minutes, and after implementing all optimizations, we reduced the processing time to 1.3 seconds. So we go to 2-qubit gates. There is a method developed by Bonsil and others, which we can call it the injection method. The basic idea here is to introduce an external anion, the blue one in the picture. So if the external anion is zero, is vacuum, so breeding vacuum does not produce anything, and all the operations here are equivalent to identity. But if the external anion is one, then the I gate, which is the identity, injects the external anion within the qubit without changing the fusion state. And after applying we apply the target gate, and finally we turn back the injected anion to its position without affecting the fusion state. So we see that the spirit of controlled gate here, but instead of one external anion, we can uh, use a double two external anions. So here we are interested about the fusion outcome of the external anions, and it is the same logic. We are going now to construct the second qubit, which is the controlling gate with these two anions, because if these two anions fuse to zero, then the controlling qubit is in the state zero, and if it fuses to one, then the controlling qubit is in state one. So finally, we have the controlled U gate, thanks to injection method. To construct 3-qubit gates, one way is to use the decomposition method, like we see here, which is very famous. And there is a theorem that says that implementing Toffoli gate or CCU gates in general can be implemented at least with 5 2-qubit gates. So 5 2-qubit gates are necessary. But in our case, we have a large fusion space. So with what we call the controlled injection method, we can use the non-computational states of the fusion space to construct more reduced 3-qubit controlling gates with 4 2-qubit gates. Like we show here, this gate that we call M of R and S. S is the target qubit. R and I are a kind of injecting gates. So the first case is we put R as assign the identity to R. So we have MIS gate. The truth table of this gate is as following. The S gate is applied if the qubit 1 is different than qubit 2. This is the numerical simulation of MIS with like we see in the left side. In the right side is the exact representation of this matrix. The green color is just the I phase, and we have the overall error of order -4. So in the second case, we assign the NOT gate to R. We have the gate M of IXS, and this gate, what it does, it applies S gate if the qubit 1 and qubit 2 are not in the same time at 0 state. So we see that it is the opposite of Toffoli or Dutch gate. So this is numerical simulation of this gate, and we see how much approximated to the exact matrix. To construct Toffoli gate, we can concatenate directly MIS and MIXS dagger, and it is an elegant way to do it. But we can do it better than that, because to reduce the number of bridges in the circuit by implementing not gates to the controlling qubit. So at the end, we have this comparison between the composition method and controlled injection method, and we see that control injection method is better in length, because the length is shorter than the length required from the decomposition method, and the error is better than the decomposition method. Here the L is the breeding sequence length of each 3 anion gate or single qubit gate. So this is my representation. Thank you for your attention. This is my team from LPMS and CQ Tech. Thank you.